Yep. Hello everyone. It's our pleasure to have Elies here to present his work about the expressivities of embedding quantum kernels. So I guess this would be one of the nice work to be have in quantum machine learning to have some kind of unifying framework. I would say. Yeah, Elies will be able to tell us more about that, and the floor is yours.
Thank you. Hi everyone. Thank you for the invitation. Very excited to be here. My name is Elies. I'm a PhD student in Berlin, and I'll be here until Friday quite late. So if the things I say excite you, or if you just want to talk in general, I'll be here. You can find me in office 418, which is a random office. And ordinary case, you can reach me over X. Yeah, this work that I'll present is a collaboration between Berlin and Leiden in the Netherlands. So we worked together with Jens and Vedran. It was a very nice collaboration. I can recommend you meet these people. And I think what I had to say. So yeah. Okay. I organized the talk a bit more like a journal club style, less as a boring seminar. So my goal for today is not to prevent you from reading our paper, but rather to convince you that you should read our paper. We leave the technical part out because it's boring. And so I split it in 3 parts, the why we do what we do, what exactly we do, and this is the important part for me, the part that I hope to convey the best. And in case someone really likes definitions and formulas and things, the minimum viable self-contained thing that I can show you for you to see what sort of problems we're looking at from the mathematical part. There will be a good time for questions here and in the middle of here, but please interrupt me whenever you want. And if this thing works, okay, broad field. So maybe you've heard parameterized quantum circuits are the best, and they will solve all quantum machine learning problems in the near term. But so we have this big goal of proving quantum advantage using parameterized quantum circuits for quantum machine learning models with classical data. So the goal of the field is to classify cats and dogs with Q better than neural networks, but we still don't have that provable advantage yet. Some people are working on it very hard, but in my part of the field of studying the learning theory of parameterized quantum circuits, for a while we stopped chasing after immediate advantage, and we've started more just characterizing the sort of things we can do with quantum circuits as learning models. And there are 3 major fields in which you can attack this problem. And for the purposes of today, we will be focusing on the expressivity. And expressivity, loosely said, is really you have your learning model is kind of a bag of functions, and you just want to ask either how big the bag is. So if you have a bag and I have a bag, is my bag bigger than yours? Or in case we're interested in very specific functions, ask whether my bag contains the function that I care about. And yeah, this is the way I think about this picture. And yeah, trainability and generalization will not really show up today. And motivation, how did we get to work on this project? And when I say what do people care about, I don't mean these are the only things people care about, but maybe you'll agree with me that these would be nice things to know. And you can either care about you have an interesting problem that you want to tackle, you just solve it with some quantum machine learning model, or you don't care about a specific problem, but rather you're into designing quantum circuits and Ansätze. So the next thing you could do is just try to come up with better, cooler, faster models for then someone else to try on cool tasks. Or finally, an interesting field is you think quantum machine learning makes no sense, people should stop getting money for this, we should start getting citations into other parts of quantum info. Then you will try to just look at what people are doing, either on the problem or the model side, and say you can do better with a quantum circuit and with a classical circuit, and everyone should forget about this. Now, I say this because in this talk, project. In this project, what we do is not any of these things. Instead, we ask like a bit more meta questions, which is really, we look back at the sorts of things we've developed so far, and we don't care too much about like specific models. The question is, do we need fundamentally new models for whatever general reason? And this is the, like, that's why, so what comes, don't expect me to show you how to classify cats and dogs. And I will not draw pretty quantum circuits that do cooler things. Just will be on like a bit of a meta plane on this search for quantum stuff. Now, the way machine learning works, quantum or not, is you're at home and you have your like selection of learning models, and you look at them, you like some of them are neural networks, some of them are transformers, some of them are other things, but you have them in like your safe environment at home, and then you go out into nature and you look around and you find a data-driven problem. You have a data generating distribution that defines the problem you would like to solve. And then the first thing you should always do is look at this data. And then you try to infer if there's like some nice structure that you can exploit, or if the functions are periodic, or you have more like sequential or spatially correlated things. And then once you've done all of this thinking, you go back home and you look through your bag of functions and try to find the one that has like a matching structure. And this usually is called the model selection problem. And because we will talk about kernels in here, particularly it's called the kernel selection problem. And the idea is that there is no one size fits all when it comes to machine learning. So like for every different model, for every different problem, you need to use a specific model that matches the characteristics of the problem to some extent. And here then the question becomes, what if you someday went out into the big outdoors and you found a problem for which you don't have the matching data, like the matching machine learning model to solve it. So like, let's say you want functions that are, I don't know, permutation invariant with a very specific subgroup of the big permutation group. Then you go back home and you look through your things and you don't find any model that matches this thing. Then you will be sorry that you did not spend more time in the past developing better, cooler, different learning models. This concept of like how the model matches the problem is usually captured by the notion of an inductive bias, which is something that's kind of hard to quantify. Like usually you stay in the loosely speaking realm. But the idea is this, like it's in our interest to come up with as much different and varied function families as we can to make sure that once we find interesting problems, we'll have all weapons possible to tackle them. And for this, kind of what we want to do is first look at the families of kernel functions that we have so far, characterize them, and consider everything possible we can do with them, with potentially the further goal of wondering whether we should come up with new ones or not. And then notice that so far I have not used the word quantum advantage. You could cast this mission in like some ulterior quantum advantage quest, but that would be a bit of a long-term goal. Not like we care more about this more immediate objectives. Now, that being said, how do we place this work in the literature? In case you have been following the quantum machine learning literature in the last few years, you may have heard that parameterized quantum circuits and quantum kernels seem to be related in some fun ways. In case you haven't been exposed to this part of literature, I will highlight some of the coolest papers, so you're welcome. And the idea is, a bunch of years ago, someone started smelling in the air that this notion of kernel methods that we know from machine learning, and this notion of parameterized quantum circuits that sometimes we also call quantum neural networks could be related. And we're going to pass. Shortly after, someone, Maria Schul, had like this super nice unifying picture of exactly how they are related in like how fundamental this relationship is. And there was this funny paper with, I think the title has been updated, but the title essentially, when it came out, was something like this. Everything related to parameterized quantum circuits is basically kernel methods. And that was a bold title. And so there was another paper whose title was also different, but like essentially the message is like not everything is just kernel methods. And these are all like super nice papers. And then here we stop asking so much what PQC you're starting from, and we start going in the direction, okay, but like what you call kernel method, is that the most general thing we could be considering? And yeah, these are like the big cool references in the field, I would say. And fun fact with this meme, I won the UHAT 2021 meme contest.
Sorry, I have a question.
Yes. I'm trying to
So I wonder what you mean by very close to kernel methods for PQC. And actually for the school paper, actually I have read it. Actually, yeah, my consideration was similar to the third point you mentioned. I think basically in her paper, he just described all the things we can describe kernel methods, and he described all these things are kernel methods. That's basically what I take away. Maybe I'm wrong. Yeah, so basically, so I wonder what's your first point. So
this one.
yeah.
No, I mean, those papers, the goal of those papers was less to establish the comparison. And it was instead, they wanted to do quantum machine learning. And they said, okay, there are two ways in which you can do quantum machine learning. Is like the neural network style, which is you have a PQC and you just optimize it. And the feature map plus quantum kernel style, in which you do quantum kernel, like you define a quantum kernel function and then do an SVM. And from our point of view, it's of course trivial and super obvious that those are under the hood the same thing. But in 2019, this wasn't trivial and obvious. And these papers are the first ones where they started hinting at the fact that this could be more related than we knew. And then shortly after, there was like this treaty saying, look, this is in the way they are related. And that's our baseline, but this hasn't always been known. If you follow Maria Schultz's papers between 2016 and 2021, you see how like the idea of maybe all of these things are the same develops implicitly throughout the papers. It's very, yeah. And so yeah, I want to spend too much time here, but like the idea is they could be the same thing in principle if we had infinite time, but for finite time, there is a gap that's presented in this paper. Right. And so we're getting close to the end of this first part that was the important part. Now I want to get into the description of the problem. So things that are clear from our standpoint are, on the one hand, that kernels, we should be interested in kernels because from the classical literature, we know a lot of cool results that apply to kernels. Like we know how kernels solve problems. We can place closed form guarantees on the performance of kernel methods, quantum or not. Then we also know how to go into how to build quantum kernels from parameters quantum circuits using these notions of quantum embeddings. If what I'm saying makes no sense, don't worry. We'll like eventually lay it all out clearly. And then my question had always been, okay, sure, there's this way in which you build quantum kernels, but what about the other ways to build quantum kernels? And we had to refine a bit the question in that not only do things exist, but rather should we care about kernels that don't come from quantum embeddings? And now the statements that are true about our field is that we have this one way in which we know we can build quantum kernels that I'll also explain in a second. And we just want to know if this is everything there is. Yeah, you say things in different ways to make sure we cover different approaches. Okay. Now this is kind of the question we start from. And if you know what I'm talking about, then you maybe already have some intuition on like, okay, I know how quantum kernels are usually built. I have not asked myself how else could they be built, but maybe I could think of ways. And the truth is, it's super hard to prove things, even if you have the intuition. If you don't have the intuition, don't worry, we'll get there in a second. And we have this question of, is there anything beyond? And this turns out to be a hard question to answer because you need to do lower bounds if you want to do some things beyond. So instead we ask, how expressive are quantum kernels? Like it's just two coins of the same story, and it doesn't matter how you phrase it, like we'll get to the same spot. Right. And so the questions we ask in this paper are two. The first one is like a priori, very generally, is it true that whenever you give me a kernel function, I can express it in this canonical way, in this way in which we build quantum kernels normally? And the second question is, so the thing is, like, arbitrary kernel functions are messy beasts. Like, they don't have any structure that you can use. So you start like the top-down approach, and also the bottom-up approach would be, okay, if I look at the kernel families we have from the literature, how do they fit this canonical construction? Can I easily express them in this way? And spoiler, like, I'll give you the answers to this thing, to our questions. And then if you're not interested in the details, in the technical details after this, then you can switch your brain off. And surprisingly, first, the answer to the first question is like, we can all, like, this is very strong somehow. So we have this one way of building quantum kernels that I haven't told you yet, but you can trust me, there is one. And following this one recipe that we have been doing up until now, it turns out we can always express any kernel function, quantum or not, computable or not, in this approach. And if we want to do like, and this is like the big top-down version, if we look at the more principled bottom-up constructive approaches, it turns out that we can also make everything that has been known up until now, we can make it fit nicely in this canonical construction. And if these things tell you anything, especially good are the, especially nice are this so-called transition invariant kernels and the projected quantum kernel. And this kind of a summary of our results, just to see that like everything we do in this paper is just prove different notions of universality, where we take a kernel that comes from some restricted family, and then we prove how it fits inside these canonical constructions, either with like unbounded complexity or efficiently in space, in the number of qubits, and efficiently also in quantum time. And yeah, the things like the names now will sound a bit confusing, but like the big picture idea is clear here. Like we take kernels from existing families and we just force them, that we massage them so they look like this canonical approach. And intermezzo? Yes. Oh, this is crazy. Okay, yeah, okay, yeah, now you start. I wanted to say, if you don't know me, I've been told I sound German. I've also been told I look German, but I'm not German. I'm Spanish. I'm from the prettiest village in Catalonia. I just wanted to make a little spot. It's called Horta San Juan. It's like a very, very pretty area. No one ever goes there because it's very unknown, but it's super gorgeous, super cheap, great food, great wine, great tourism. If you ever go to Spain, make sure to stop by Horta San Juan. I live very close to the
Have some discrepancy with the prettiest, but
it's okay. It is true. It's a PR. I will always. Yeah. So that was kind of the intro part. Are there any questions about what I said so far? From now on, it will more like definitions and things that might look more familiar to you guys.
you mean you are going to study like classical kernels, like using this quantum? Or?
So, good question. So we want to do machine learning, and I want to do specifically machine learning on classical data because I think it's cool. And for machine learning, there's something called kernel methods, where you take a kernel function, and then with this you have like a deterministic way of solving a classification task. In our case, we'll do quantum machine learning, in that the function that we will use, the kernel function, we will need a quantum computer to evaluate it. So we will do.
You want to evaluate the classical function with the quantum computer.
What is a classical function? It's not a very well defined concept. I will evaluate a function that takes classical inputs and produces classical outputs, but you need a quantum computer to evaluate it efficiently.
So embed quantum into classical data. In quantum, it's also classical data.
I mean, Shor's algorithm has classical input, classical output, and it's a quantum function. So we will not do Shor's algorithm because it's not a kernel function, but we'll use kernel functions that take I mean, yeah, it's the next definition. But you take classical inputs, produce classical outputs, and you just need a quantum computer to produce the input-output relations. I can give you the computational complexity definition later if you want, but it's not very interesting. Any other questions? I think I say again, what we say up until now, to me, is like the interesting part. So you feel free to ask any part, any detail that was not clear. Because the moment we start with definitions, things will get.
Yes, I have a question. It's more like I came across a paper before. I think it's in classical. It was something along the lines of like every gradient-based method is a quantum, like is a kernel machine.
Yeah.
Is like the proof for quantum similar to that classical?
There-
Like if you know that.
It's a, yeah, I think I suspect what you mean. And no, the proofs will have nothing to.
Okay.
So because there are these proofs to study big neural networks where you turn them into kernels.
Yeah.
And then you use guarantees you have for kernel methods. And there the goal is to understand better how the neural network works. Because our goal in the end will just be to see what we can write in this form. The way in which we will do things is a big deal. And also the objects from which we will start will not be neural networks, but just other kernel functions. It's a bit different. But the same thing, like this is called the neural tangent kernel, and there have been proposals for quantum neural tangent kernels to kernelize quantum neural networks. Like this exists, but this has nothing to do with what we do.
Oh.
More questions? Great. Then. So now I start giving you things that we can discuss. Let's say you want to do binary classification like this. And let's say the task you want to solve is kind of easy because the two binary classification means we have two classes, red and blue. And let's say this task you want to solve is very easy in that like there's a linear separation between both classes. Then for linear optimization, you might know, or if not, I tell you now, that you can solve this problem by considering sums of inner products. So like here the xi are the data I give you to train. Like we're doing machine learning, so we have some training data, we want to find the solution, and this has to perform good on new test data. So these points here are this collection of xi, yi. And in order to find this separating plane, it turns out it's enough to consider models that are of this one, where you take sum of inner products with some weights, and then give up shift. And because we're doing binary classification, you just put a sign function on top. And if this sum gives you something positive, you call it red. If it gives you something negative, you call it blue. And tada, you did machine learning. Congratulations. Now, if you have a slightly more difficult problem where you don't have this linear separation, for example, this one here, then this thing kind of breaks, because if you want to consider models where you only take sums of inner products with some weights and a shift and a sign function, then you're restricted to only do linear cuts. And if your data cannot be classified with a linear cut by construction, then you're out of luck. And so what you can do instead is you start from your original data space and you can add dimensions. Like you can come up with some map that for each of the points adds some more information. So like you, in this case, you go from 2-dimensional data to 3-dimensional data, where the third dimension is kind of artificial. You put it there on purpose. And this, what we call this phi map. And there, if you do this in a smart way, if you add dimensions in a way that eventually makes that your two classes are linearly separable, then you can do the thing you did before again. Now, just now, instead of working on the original space, you will work on a new space where you have mapped your data. But the idea is the same. You will only, you're guaranteed to succeed by only taking inner products with some weights and some more shift and a sign function, given that the way in which you added dimensions was smart. This is just like typical linear optimization problems. Should be, if not familiar, at least not surprising. And this is usually the way in which kernel methods are introduced in textbooks. This is where we started from, and now I just give names. This phi can be called a feature map or an embedding. Now the map goes from your original data space, X, into something that needs to be a Hilbert space, because you need to have inner products, otherwise you cannot do the strategy you need to follow. And then you just do a quick change of name. The inner product of pairs of feature maps, now you call kernel function, and it has to be the inner product corresponding to the Hilbert space. And boom, you did kernel methods. So everything is the same, like you still have the same data problem classification that you're still mapping somewhere else, and you're taking inner product. Just you decide to call the inner product function a kernel function. And this again gives you all the guarantees to find a good solution to your problem, with good generalization, good everything, deterministically. So it's like a dream of machine learning. And so this is one way in which you can construct kernel functions, but mathematically, kernel functions have like an actual definition that doesn't depend on feature maps. And they are functions that take pairs of inputs, produce real numbers. You can also do it complex, but and which fulfill two properties. They're symmetric under exchange, so it doesn't matter which input you put first, you always gives you the same value. And the intuition here is that the kernel function wants to be a similarity score. So like you put two things and the kernel function tells you how similar they are. So it should not matter which one you put first, because the way in which they are similar should be the same. And then there's a very annoying property called positive semi-definite, which let's not get into. It's just, we don't need it. It just means that if the kernel function was a matrix, it would be positive semi-definite. Okay, so this is like a mini intro to kernel methods. I just gave you the middle definitions. Now let's bring in the quantum machine learning. If you've read any of these papers, you'll have learned that what we do in quantum machine learning in the end is like a very simple process. We have a quantum computer, we initialize it in an easy state, and we are able to measure an easy observable. And so what we do is we prepare a quantum state that depends on our input data with some unitary. Parameter is unitary, take Elies rotation gates and put the parameter to be like some components of your input, and boom, you have a data dependent state. And from the other end, you do this backpropagation of taking the observable and making it trainable. Like you make a data dependent state and a task dependent observable. And then you just take their inner product, which is a different way of saying you measure the expectation value of the observable measured on the data dependent state. And formally, this is nothing but the Hilbert-Schmidt inner product, which is the canonical inner product for Hermitian matrices, of which both are Hermitian matrices. And then to bring it into the same perspective as we had before, we wanted to do binary classification. So you take this function, you put it inside a sign, and that will give you the class. Like if it's positive, you would say in the same problem that you have like class red. If it's negative, you would say you have class blue. And you've done quantum machine learning.
For example, what will be the O here? So you
here it would be like just polish that on the first qubit.
I see.
I mean, it could be anything you can do in the lab. If you want to do it formally, you will allow for very general things. But usually O would be something very local, very easy. If you want to do a bit more complicated stuff, then you can consider sums of local easy things. But the idea is you have a easy observable, and you complicate it by turning it into a funny thing with the parameterized gates. But ideally, the complexity of the problem will be held in the variational part and not in the thing you measure in the end.
Last question.
Yes.
So the X here is a discrete variable or continuous variable. I do not matter.
Could be either. I mean, for the definitions right now, it doesn't matter because I let it depend what this is. It's up to you. Yeah, no, and I think later on it will not matter. I think of it as continuous because I'm a very happy person, but if you want to think discrete, it's completely fine. Right. More questions? This is an important thing to understand. Okay. But if you've been paying attention, you'll notice that I said things that should have triggered thoughts. So the way I described doing quantum machine learning with parameterized quantum circuits was by taking data, mapping it to something that's of very high dimension, like exponential dimension in the number of qubits, and then doing something linear, this should smell like a kernel to you, because that's what I described we do before. We have like the embedding or the feature map, and then we just consider inner products. And so in this one paper, Marie showed like where she presented the relationship between PQCs and kernels in a very formal way. There was this idea introduced that you can do what I said before, which is prepare your data-dependent quantum state and then measure a task-dependent observable, or you can just take an inner product between feature maps, which happens to be a kernel function, and then just do kernel methods using this thing, where you don't care about the variational part. I mentioned variations paper. This figure is taken from Sofian's paper, the one where not everything is quantum kernels, but the explanation should be very good in both. And so there's this fact that, as we were saying, that from our standpoint is obvious, of course, but it's still cool conceptually that we have these two completely different approaches of like what people call quantum neural networks and what people call quantum kernel methods, which feel very differently, because in one you have gradients, you optimize things, you have overfitting, you have problems. In the other one, you just evaluate a function on pairs of points and then you deterministically have an answer. Happen to be super deeply related under the hood. We have a little picture. So the way I think about this thing is always, we have our initial data domain. We have 2 points, blue and orange. We have, the way I think of the quantum embedding is less like a quantum state and more like a function from my input domain to the space of all possible quantum states, where like the pair of points is mapped. And then once I'm here, the only thing I do, like this last part is like the easiest thing you could do. You just measure the inner product of these 2 million objects if you want. And the happy coincidence is that the canonical inner product on the space of Hermitian matrices is just the thing you can measure in labs. Not easily, but realistically. And this, because it depends so heavily on the quantum embedding, is what we call an embedding quantum kernel. And like on our title, we talk about expressivity, blah, 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 embedding quantum kernels. When I say an embedding quantum kernel, I mean something that looks like this, trace of rho x prime. And this is what I described to be the canonical. You look and read in the literature, except very few exceptions, every kernel that has been proposed to date is of this type. It's great because it's very well justified, but then my question was, is there more? And there's one added reason why considering these things are great, and it's the so-called representer theorem. And if you haven't heard it before, this might be surprising, but there are these 2 ways, right? Like there's a quantum neural network way and there's a quantum kernel way. They work completely differently. They are able to realize different functions. Like there is this gap in that there are some things that the kernel can do, which QNN cannot do, and also the other way around. But we have this guarantee that what we can do on the training set, so the thing we use to reach the solution, the performance we can reach on the training set by the direct optimization, this is like the QNN approach, is lower bounded by the training error we can achieve using kernel methods. So this is very strong. As long as you fix the quantum embedding, anything you can do with a quantum neural network or with a parameterized quantum circuit is at most as good as what you could do with a quantum kernel. This is like deep, and this made it very counterintuitive to say that not everything is quantum kernels. I will say it again. We are competing. We are given a fixed quantum embedding. This is not up to us. You have a super powerful, super IBM, Riverlane, Xanadu, everything combined supercomputer quantum, where you can implement any parameterized observable. And I just have the ability of computing fidelities of these things. We're given some training data from somewhere, and then we're asked, okay, find the separating hyperplane for this task. Then anything you can ever do is at most as good as what I can do. And my thing is deterministic, doesn't suffer from like trainability problems, it always just gives you the answer. So that's like very, very, very cool. So, and this, in case you're less familiar with this part of the field, this is one of the reasons why people care so much about kernel methods. It's because like we have very strong guarantees for wide neighborhood. And yeah, this is why you should care about kernel methods. Now, this fact that's clear but cool, I summarize it in like this sentence. For any embedding, there always exists an embedding quantum kernel. So all embedding quantum kernels are embedding. Then the question we would like to ask in different ways is the reverse. Are all quantum kernels also embedding quantum kernels? Because if they are not, it means we have found a non-embedding quantum kernel. And this is kind of the thing we were looking for, something that's outside of the canonical approach. This might be a bit weird, but I explain the way I think about it. It's like on the one hand, I have kernel functions, which are functions which are guaranteed under the hood be able to be expressed as an inner product of feature maps. This could be infinite dimensional, could be uncomputable, but all kernel functions admit one such expression. And on the other hand, I have what I call quantum functions, which, for example, could be something of the type you prepare a state and then you measure something. Now, embedding quantum kernels live in the intersection of these two things because they are an inner product and because I can run them easily on my little computer in which I prepare a data-dependent quantum state and then I measure something. So clearly, embedding quantum kernels are quantum functions and are kernel functions. But the question was, are there other things which are quantum functions and which are kernel functions but are outside of this family? And this is just a different way of saying the things you said before. And yet another way of asking the same question is, if I give you a kernel, which can be quantum or not, can you always find a feature map that corresponds to that kernel? And there's some intuition for why the answer should be yes, and some intuition for why the answer should be no. It clearly should be no, because I'm restricting what type of embeddings you can use, in that I'm asking you to use only quantum embeddings, which should be a restriction. Maybe there are other things you could use, like infinite dimensional stuff. At the same time, if you try to prove that something is not an embedding quantum kernel, you will have to prove that there doesn't exist a quantum embedding kernel. And one thing that you quickly find out when you work on these things is that even a single kernel, there are infinitely many different feature maps that give rise to the same kernel. So proving inexistence is like very hard. And if you've read quantum machine learning papers, you will have noticed that a lot of the things we do is just we read a very good classical machine learning paper, then we put quantum somewhere and publish it. But we cannot do that here because in the classical community, this notion of a classical embedding kernel would make no sense because kind of the Hilbert space of classical computation is something we don't usually think about. Like this notion of encoding real data in a bit string that is supposed to mimic the effect of a quantum state. It's kind of strange, people don't do it because it would not give any advantage. So we're kind of alone in that we need to come up with genuine new ways of proving things. And maybe by now I've convinced you that even though there are some reasons why you would maybe not ask this question, because who cares? Just let's run things and see how they go. I hope I've given you a good idea that this is a natural question that someone could ask, because why not? I agree that in the end, this is still at the meta level, because even if the answer is yes or no, I will not give you a new flashy toy that you should just go outside and use. Sorry, that was not the goal. But depending on what answer we find, we will have established like the absolute limits of what is at all possible, which I find quite exciting. Okay. We're almost at the end. This thing does whatever it wants. Okay, we're almost at the end, and I want to briefly elaborate on this idea of why I find natural to ask the question whether there's something beyond embedding quantum kernels. And it's really about efficiency. So here I present you two classical kernels. It's the first time I show you any kernel, so you should be excited. I put there because I didn't know where to put it, like we're considering d-dimensional data. And on the one hand, we can just take your typical inner product and then put some power. Or there's this thing called the Gaussian quantum kernel that everyone loves. Now, if you look at these things, they don't immediately look like an inner product of feature maps, right? This is almost an inner product of feature maps, but it's not really just inner product of psi x prime, because we have the exponent, and that could mess things a bit. And now I will ask the question, okay, how do we evaluate these things? And if I gave you a pocket calculator and I asked you, please compute me this function for 2 given x's, you would probably need to do these many operations. Like you need to do the products of these things and then the sums and then the power. So you'll have something asymptotically like these many operations, which is not many. Like this would be an efficient thing to run in your computer. But there's another way in which you could run it, which is, what if I told you that I know the recipe of how to turning this expression into an embedding classical kernel? Like I can show you how you can take the components of X and combine them into a larger Euclidean object, which you can then just take the inner product of them, and which would give you exactly the same function, just computing it in a different approach that would feel a bit more. But then you would find out that the dimension of this feature map for this kernel corresponds to just computing all possible monomials up to degree R of all the components of X, which means the size of this feature map is combinatorial, is like R choose D or something. So if you wanted to evaluate this function by first building the embedding and then taking the inner product, you would end up needing combinatorially many operations, which is much more than this question.
This polynomial kernel, for example, is not bounded and like any value, but your kernels are just the trade-off to
They will be bounded, yes.
the matrix was bounded by 1. This does matter.
Not for this. I mean, I think you could bound this, like you could divide by something. Like, let's say my data doesn't come from all of R, but it comes from like -1 to 1, then this is also bounded.
It doesn't matter, like if
Not a priori. Yeah, so I show you these 2 ways in which you can compute the function. One of them would be like, it's a so-called the kernel trick, because even though this function corresponds to a big inner product in some Hilbert space, we know a secret way of computing it cheaper than it would take to just build the whole embedding and then taking the inner product. And this is one of the reasons why it would be cool if we had something that's not an embedding quantum kernel, because what we do now in practice is really build the feature map as a quantum state and then taking the inner product. So it's in the style of option 2. And so the question then would be, maybe there is something hidden somewhere so that we can compute things in the style of option 1. And just the extreme example of this thing, if we take this Gaussian kernel that we use for many things, one way in which you compute this is just by taking this norm and then the exponential, and like I'm not sure how much an exponential costs, but it would not be super much, right? Like we have this direct way of computing the kernel, which would be great. And then if we consider the other option, like the building the feature map, you might be surprised to know that the feature map that corresponds to a Gaussian kernel is infinite dimensional, because it's all monomials of unbounded degree of the components of X. So if you want to do this second option, you better take a day off or something, because it will take you infinite time. So there are limiting examples in which really forcing ourselves to build the feature map could really mess things up, essentially, somehow. And yeah, just we're getting close to the end, even closer. The question we had before, now with nice notation, is given a kernel K, is there a quantum embedding rho of K such that the kernel is approximated by the corresponding embedding quantum kernel? Answers, candidates? Yes, no, maybe, sometimes.
yes.
Yes, he's read the paper. We distinguish 2, I mean, I told you before. But in one case, yes, always, because I only ask if there exists something, and whenever there's an existent question, the answer is yes. But can we find it efficiently? Then sometimes also yes, maybe not always. And I very briefly discussed the point number 1, and for point number 2, I'll just drop the keywords and I will not try to explain them. So given a kernel K, is there a quantum embedding kernel, rho of k, such that there is some sort of approximation? We say the answer is yes, and it's yes in a very unsatisfactory way. We go to the classical literature, and there's this thing called Mercer's theorem, which says that for any kernel, there's a classical embedding that reproduces the kernel. So we just go to the classical literature, take this existence proof for classical kernels, and then we say, but quantum computing is universal. Whatever this classical vector is, because these things are guaranteed to be normalized, I can just map it into some quantum state in a special way that will guarantee the inner product to be somewhat similar. And boom, it's kind of, I didn't give you anything constructive in how to build these things, but I build the question. For any kernel, there's something I could run that guarantees that there exists a corresponding embedding quantum kernel. And this is what we used to say that that all kernels can be expressed as embedding quantum kernels. And of course, for this to be less unsatisfactory, we need to add some notion of efficiency, because these things could be like, the only thing we have guaranteed is that it requires a finite number of qubits, but nothing else. We don't even know about like finite time.
Sorry, I have a question over here. So like for some of the kernels, we would have symmetries, right? That they will respect some kind of symmetries. I'm just wondering whether this kind of like approximate process will preserve those kind of symmetry, or maybe just preserve
It
some.
doesn't need to.
Doesn't need to.
Well, as far as I know. I mean, this constructive approach of Mercer's theorem uses like the integral kernel operator, and it moves out from like your regular Euclidean space and gets into the RKHS, like the reproducing kernel. Like it moves into a space of functions where the kernel itself evaluate like with one fixed x and the other x free becomes the feature map itself. And I'm not sure if this RKHS for a symmetric kernel would result in a symmetric kernel itself. Okay. In a way, all kernels respect some sort of symmetry, because even if you take like a regular Euclidean products, those things are rotation invariant. If you rotate both vectors in the same way, nothing changes. And some other kernels that are based on distance metrics, those are translation invariant. If you're measuring the distance between 2 points and you move them, the distance doesn't change. So because kernels are a similarity measure, you can think of the similarity as leaving out all the redundant information and only keeping the important ones. And so the function itself will retain some symmetry. I don't know if the feature map themselves will retain any other sort of symmetry.
So we should look at the kernel instead of the feature maps.
Yeah, but yeah, in the end, the guarantee is that the final inner product ends up being almost the same as the original kernel. So whatever functional structure that we had here, we'll also have there.
I have a question.
Yes.
So for x here, it should be real number, or it's always real number. Okay, I see. I see. I see it. Yeah. And then it's good now. Good.
Wondering, it's quite an old thing, but it's by Schmidt and part of this. I think it's maybe related to Mercer's theorem, just kind of going straight to the quantum. And I think they also have a minimal construction, but then translating it into anything that can be done in a lab, I don't know.
I mean,
It's very
here it's not, the implementation is not on the room. Like this is nothing you would ever run in your lab. It's just something that you can massage into trace of rho x prime. And we also aim particularly at minimal constructions, which is just existence with finite resources. But I'd be interested to see this reference you pointed out.
Now coming to think of it, we have trace of positive operators now.
Yeah, like there's a lot of without laws of generality going on. You can rescale things, you can normalize off shift. That's why here it's not equal, but for the machine learning purposes, all of those things are not a problem. Right. Question? Any other questions on this part? Okay. we will end up in a high. I said we need to add efficiency, and when you need to add efficiency, you need to be careful, because in this sort of question, we have super many moving parts. So I will just obliterate your attention span by dropping the big question with all fleshed out definitions. And then if you want, we can talk about it later, but it would be a bit much now to check. Okay, question, expressivity of embedding quantum kernels. We want to talk about efficiency, so we need some scale parameter and some sequence of kernels. Well, I will talk about a kernel, but deep down I mean a sequence of kernels where you can scale up like the input dimension or something like that. And the input to this question is the kernel or kernel sequence and some precision parameter. And I will give you 3 properties that are defined in all glory, but let's not go through them. I said that a kernel is quantum efficient if I can run it on a quantum computer. And I say that a kernel is embedding quantum efficient if I can run it as an embedding quantum kernel. I can prepare the feature maps and just take their inner products. And I would say that a kernel is classically inefficient if I cannot evaluate it without I cannot evaluate it using a classical computer only. There are some definitions. I would encourage you not to read the fine print. So then the proper way of asking our question, now that we want to put efficiency, is if we have a quantum kernel, which means a kernel function that's quantum efficient, does it follow that if a function is quantum efficient, then it also is embedding quantum efficient? Like, does there exist maybe a different quantum embedding that results in the same thing? And we put classical inefficiency because if there was a conspiracy and the answer was yes, but also classical inefficiency, then we would look like fools, and we don't like to look like fools. But that's not so important. Okay, this is a question where last day this is where the meat of the paper starts. And just to show it again, because now you have better tools to understand this thing. On the first part, like for this theorem, one of the first results, I have shown you the proof bare bones, how this thing works. For everything else, we follow a similar approach in which we take this kernel functions, which can be either quantum or not. We put them through a super cool algorithm that I recommend you find out called random Fourier features, which kind of gives you an approximated low-dimensional embedding to approximate whatever kernel you have. And then that thing, which could be classical, could be exponentially big, we don't know. We just use the Universitat of quantum mechanics to make sure that we end up with either polynomially many qubits or polynomially long time in total. And there's this friend here, which is super cool. If you've been reading the papers of Robert Huang, one of these information theoretic guarantees for machine learning advantages, there was this projected quantum kernel proposed, which relies on classical shadows, and it's very good. And it's something that manifestly does not look like trace of rho x prime. But by looking at things and trying to figure out whether that was an embedding quantum kernel or not, we found a constructive, nice way of just approximating it to any precision as an embedding quantum kernel. So to our surprise, everything we tried, and we tried everything that has been proposed in the literature, everything turns out to be an embedding quantum kernel, either efficiently in time or efficiently in time and space. No, either only efficiently in space or also in time. So pretty cool. Just to summarize, I've said the same things a bunch of times from a bunch of ways, but let's have a clean image to go back home. I've described how embedding quantum kernels, which are the thing that we've been using so far, are well justified. There's good reason to use them. I've also motivated that even though there's good reason for using embedding quantum kernels, there's nothing that prevents us from trying to come up with quantum kernels that are not embedding quantum kernels. And then our results kind of were a bit sobering in this direction, in that we kind of tried to find such things. And for everything we tried, we always managed to find a way of provably writing every possible kernel as an embedding quantum kernel, both top-down for in general and bottom-up for efficient constructive approaches, which was kind of cool. And what does that mean for you? like tomorrow when you wake up, what should you think about these things? On the one hand, nothing changes. Like if you were not using kernel methods, I'm not giving you anything. If you were using kernel methods, chances are you were using embedding quantum kernels, and our results kind of say that you're doing fine. You can keep using embedding quantum kernels. But at the same time, we really looked very strongly into non-embedding quantum kernels. So if you do quantum kernel methods and you find something that's not an embedding quantum kernel, please let me know. I'll be very thankful. And the references one because they're very cool. And thank you for your attention. I'll take.
Yep, cool. Thanks, Elias, for the very interesting talk. And yeah, you just like really attract out all the like it's kind of like derivations and give big pictures. Is like how presentation should be.
Yeah, please, everyone read the paper.
Yeah,
It's a very good
yeah. And yeah, so for the audience from the Zoom, you can unmute yourself or type questions in the chat to like ask the questions. And any question from the audience here? Maybe I could ask one question. So for quantum, like for kernel in general, right? Typically we would kind of refer to is like efficiency, like the efficiency of evaluating a kernel is basically depends on the number of data points, like because it's still at n squared, right?
Yeah.
So I think like for this embedding quantum kernel, it also face the similar issues.
Same.
Basically for classical kernels, they like for like shift-invariant kernels, they would use like random Fourier features to basically have efficient approximations. I think it's like that you can also use the same things over here to kind of like break the to reduce the number of evaluation that you need over here.
That's a very good question. Yeah. So I've been saying that kernel methods classified in quantum are great. We have all the guarantees in the world. So why is GPT in the news and not kernel methods? It's because the time it takes to train and evaluate a kernel function scales a bit worse than neural networks. Like neural networks are conjectured to work in linear time. And in practice, they seem to work in linear time, whereas kernels need cubic to train and quadratic to evaluate, which is just a tiny bit worse, but it's bad enough that you don't use them for big data things. Now, throughout this talk, I haven't really told you what you should use your kernel for. So the way I approach it is like you have your reasons to use your kernel, and I'm just kind of this annoying guy in the background saying, but you haven't considered evaluating it this other way. And in my mind, like in the end, the way our results work are only in terms of function approximation. So you have your function, you want to use it for whatever you want. I only tell you whether the way you're evaluating your function is the best way or not. So how many times you need to call this function really doesn't change here. And regarding random Fourier features, again, there are two ways to approach random Fourier features, which are very different. The one I'm most familiar with is also in the direction of function approximation. So you have your Gaussian kernel, which is not very expensive, but it grows, like the complexity of the Gaussian kernel, of evaluating it once, is roughly the dimension of your data. And if you have images, then the dimension of your data is thousands. So you don't want to use it. And then with the random Fourier features algorithm, what you do is you reduce it to something that's smaller than the number of features you have. But in principle, this only reduces the complexity of evaluating it once. It doesn't change how often you need to evaluate it. So even with, at least with the original usage, the original proposal of random Fourier features, the sample complexity doesn't change. So you still have the quadratic approximation. Then there's another way which says, forget about your kernel, forget about your neural networks, use this intuition for why random Fourier features work to build a new model that just works a bit differently. And there, I guess, you can do things with gradients. You don't need to evaluate kernel functions, and you can get away with linear complexity. But then you kind of stop doing kernel methods. What you do in this other way, you have your kernel. From your kernel, you go to the approximated random Fourier features kernel. You realize that the Hilbert space of the approximated kernel is low dimensional, then you do explicit optimization on the Hilbert space, which is low dimensional. So that then you rewrite it as a shallow neural network. And there you have a neural network. So you will not have quadratic scaling.
Right.
So it depends what you mean when you say random Fourier features.
Okay, I see.
But this is like a super interesting, like there have been a bunch of papers recently on random Fourier features for quantum kernels.
Yeah.
And they are more of the second type. I guess we use random Fourier features more on the false type, but it's just fun to see how things work. And I suspect this has not been the end. Like there will be more applications of random Fourier features to quantum kernels with cool results, on which I'm not working. This is not
So
a
you're just like
this is
looking
not a
for-
foreshadowing.
Yeah.
Yeah.
Okay. Yeah, maybe I could. Oh, yeah.
Hi, could you give some examples of these quantum kernels commonly used?
Yeah, sure. I mean, let me just go back to the picture. Whoa. Okay. If you do parameterized quantum circuits, here I've been restricting ourselves to these quantum circuits where you separate physically the data encoding step from the observable measurement or the trainable step. And here, the first thing you could try is this thing called amplitude encoding, where you take your data and you normalize it, and you make it so that like the ket, like the quantum state that results after you somehow has its amplitudes proportional to your data components. So it would be like sum over I xi ket I. This is one thing you could do. This is not very appreciated in the community because we found that this can lead to at most quadratic functions of your inputs. And it could be that your problem is not linearly separable with quadratic functions. Another thing you can do is using these Pauli rotations. It's called rotation encoding. So you take a bunch of Pauli rotation gates, you organize them in some way, you could put C nodes inside if you want. And for each of those, you put one of your components into the parameter of the Pauli rotation gate. It's called rotation encoding. And this you could even make it trainable if you want. But it kind of breaks the picture here a bit. And that results in kernel functions, which are like trigonometric polynomials. So your function in the end ends up being kappa of x prime is a sum over cosines and sines of x and x prime summing and subtracting. Yeah, and like there's this whole Fourier picture on how to represent the quantum kernels that come from this rotation encoding as feature maps, as trigonometric polynomials. Then for one of the original papers by IBM, they used this IQP encoding, which is used for quantum advantage sometimes. And there you have like a combination of both, where it's a bit like rotation encoding, but where in some of the gates you encode products, like monomials of your input data, and that gives you access to some other type of functions. And for continuous variables, you can also do it with squeeze states, and then take the inner product, and then it looks like Gaussians and plus non-Gaussian terms. I think this is, I guess, most of it. Yeah.
Maybe one more question from me, like because currently the typical kernels that I saw like in the literature, they are doing unit trees, right? But then eventually we can use quantum channels, like parametric channels, and what do you think about that?
So I'm a very happy guy, like I'm not very practical. In our proofs, we use funny looking channels in that we have this step in Mercer's theorem. So yeah. So the way in which we take a classical vector and produce a quantum state that respects the inner product is not by doing amplitude encoding or anything like that, because it would give you an extra square. It's by preparing a state that is a like, so you have a density matrix, permission operator. You can take a Pauli basis, which is a orthonormal basis of permission operators. And then you have a quantum state needs to be trace one. So you cannot change the so if you want to, so any quantum state expressed in the Pauli basis has a one for the identity term. But for every other term, same, as long as you have everything to be one norm unity, you can just put whatever in there, and that will be a quantum state. So we just take our one norm unitary vectors and put them in the Pauli basis.
Be very careful to.
Yeah.
I struggle with this always. I just my.
No, but like we have this one proof that if you do it this way, then the thing is PSD. I mean, if the vector, so if you have a vector B, which is one norm normalized, then you can create a quantum state that's identity plus some each component of this vector times any Pauli word without repetitions divided by 2 to the n.
This is positive.
This is positive.
Let's go.
I told you should read the paper.
No, it's not true.
Into norm is not true. And there's an easy example. You take
What?
one norm is true. The one norm is smaller than the two. There's like Bell inequality.
No, I was thinking about two norms, sorry. So.
No, it's one norm. I mean, and as pointed out by our lovely reviewers for our KP submission, the way to think about it is that you just, if you encode it only in the diagonal, if it's one norm normalized, then it is positive semi-definite by necessity. And if you just also want to use the off-diagonal terms, then you end up from a 4 to the n dimensional object into a 3 to the n dimensional object or something, but it doesn't change much.
Okay, cool. Yeah. I think we could end our seminar now, and yeah, thanks Elias for the very interesting talks. And thanks everyone for your time, and see you next week.